All right.
Recording in progress.
Okay, first thing, what is wave? Wave is actually transfer of energy and momentum from one point to another. But wave is not the transfer of mass or matter. So trying to tell you, look at this diagram. Water wave is moving from here to here, right? From left to right. So whichever particles here, they remain here, they don't go here. So they will just transfer the momentum to the water particles and the energy. All right. So wave is transfer of energy and momentum from one point to another, but not the transfer of mass or matter. Okay. How do we create wave? All the waves that we're going to discuss in this chapter, we'll be discussing light, sound, all the electromagnetic waves. Light is electromagnetic wave. All the waves that we discuss will be, or any wave that we're going to discuss will be created by vibration. A repeated motion or oscillation, vibration. Only a repeated motion, vibration, oscillation, okay, will be able to create a wave. A wave must be created through vibration. Okay, next. What are the characteristics of waves? When we talk about waves, you should know, all right, every wave on the surface of wave, as they transfer the energy, the particles are sending it, all right? So there'll be an imaginary line we call wavefront. So wavefront are points on a wave where if you choose VW here as a wavefront, this is a crest line we call it. So all the particles on this line will be vibrating in the same direction. So wavefront should be an imaginary line on a wave where the particles along that line actually are vibrating in the same direction. All right. So PQ is a crest, and this dotted line will be a trough. Okay. So this trough here. So if you choose a wave front of trough, the particles along that line are vibrating the same direction, like going down here. VW crest like going up. Okay. So wavefront will be an imaginary line where particles on the same phase or same point or same line vibrate in the same direction. Okay, next. This is a straight wave, right? So we call this plane wave. Plane wave, they're moving in one direction. Okay, we also should know that there are progressive wave and stationary waves. Stationary waves, they create a wave profile that does not propagate with time. For example, string bass. String bass. If you take a guitar, string bass system, the string will vibrate between the two ends which are locked or tied to the guitar, right? So that's called a stationary wave system. Progressive wave, like the sound wave and water wave, which is moving from one point to another. All right. So these are the two types we have to know: a static system, stationary, and a progressive wave, which is moving up, right? Okay. When waves are moving, we call it propagation of wave. Okay, any wave. When waves are moving, we call the movement of wave as propagation of waves. So there are two ways to look at propagation of wave. You look at it as transverse waves and longitudinal waves. Okay, transverse wave will be the idea where waves are moving, let's say on this diagram, waves are moving from left to right. So direction of propagation is left to right. But the particles will vibrate up to down. As the particles are vibrating up to down, we realize that direction of particles vibration perpendicular to the direction of propagation of wave. So when the direction of propagation happen to be perpendicular to the particles vibration, this whole wave are called transverse wave. So transverse wave, transfer wave, for example, water wave or electromagnetic waves, all are transverse. Direction of wave propagation will be perpendicular to the particles vibration. Then what is longitudinal wave? It will be direction of wave propagation will be parallel to the particles vibration. So direction of wave propagation will be parallel to the particles vibration. So for example, sound wave, these are the particles that will transfer the momentum, move and experience collision, bounce back. Collision, bounce back. So as the waves are moving, directions of wave propagation happen to be parallel to the particles vibration. Example is sound wave. And also during earthquake, we realize that the seismic wave, can be longitudinal. Okay. Right? Okay. Any questions so far? If there are two types of graph used to explain and show wave, the displacement time graph and also the displacement distance graph. Okay, we start with the first one, displacement time graph. When you look at displacement time graph, okay, you should know that on this graph, if you look at it carefully, right, the axis Y is displacement, axis X is time. So we are able to determine period. See here, this is the time taken for one complete oscillation, right? So this is the period of a wave. All right. So on a displacement time graph, we are able to identify the period of the wave. All right. And we must know the relationship. Period is equal to 1 over frequency. So frequency will be equal to 1 over period. So frequency represents number of oscillations per second, number of repetitions per second. All right. Period, time taken to complete one complete oscillation. So on the displacement against time graph, you're able to identify, right? Number one, the time. So we can calculate the period, so we can calculate the frequency. We also able to identify the amplitude of the wave. See, this is the amplitude. This is the amplitude. So amplitude will be the maximum displacement of a wave. What is amplitude? The maximum displacement of a wave. All right. So up and down, it's still amplitude. We also able to identify the displacement. This is displacement. This displacement. So displacement is movement of a wave away from its equilibrium point or point rest. This is the point rest or equilibrium point. So how they are displaced? So in a displacement time graph, we are able to identify period, calculate frequency, identify amplitude and displacement. So this graph is very important. Next graph will be displacement distance graph. All right. In a displacement distance graph, what can we identify? You see here. All right. We can actually identify, all right, in this graph, we will realize that we can get the wavelength. See the wavelength? This is the wavelength. The distance between two consecutive points in phase. All right. So for example, if I take the distance between this crest and the next crest, so this is the wavelength, lambda. All right. We also can actually identify from 2 to 6, right? This also wavelength. All right. So when you have a displacement distance graph, you are able to identify the wavelength. You also can identify the amplitude. See, this is the amplitude, right? This is the amplitude. This is the amplitude. We can get the amplitude value. We also can, if we can get the amplitude value, we can identify the displacement. So this is the displacement, all right? Maximum displacement is amplitude. Amplitude will be the maximum displacement. What is maximum displacement? Amplitude. This is amplitude. This is the displacement, amplitude, right? This is the amplitude. So the whole idea here, on a displacement distance graph, we are able to identify wavelength, lambda, and then amplitude and displacement. Okay, what is the relationship between all these? Okay, earlier we know the earlier graph, we know the frequency, right? So speed of a wave is always equivalent to frequency times lambda, speed of a wave. And also period of a wave is always equals to 1 over frequency, and frequency equals to 1 over period. Right? Okay, done. Okay, two important things here. As a wave propagates, any wave that's moving from one point to another point, the wave will undergo loss of energy. So as a wave propagates, all right, a progressive wave, even a non-progressive wave, as a wave is moving from one point to another, we realize that the wave will undergo a process of loss of energy. So due to loss of energy, the wave amplitude will decrease. So during the process of loss of energy, which we call damping. So damping is actually loss of energy. What is damping? Damping is actually loss of energy. All right. Damping will be loss of energy. Okay. So there'll be two types of damping, external and internal. So what is external damping? So any system vibrate, a spring system or any plastic system, whatever system vibrate, they will experience external resistance due to air resistance. So external damping, loss of energy to overcome frictional forces or air resistance. External damping. Now, what is internal damping? The object that is vibrating, inside the object, there will be particles, there will be molecules, and these molecules will be the molecules will undergo compression and stretching. So as molecules in a system undergo compression and stretching, as molecules in a system always goes through compression and stretching, what happens? There will be forces, okay, of extension and compression. So what happened? Loss of energy to overcome the force of compression and stretching. The forces of attraction and repulsion. Same, right? So internal damping, loss of energy to overcome these forces, right? Any question? These are the ideas. So we have damping, internal damping, external damping. If you see the graph, you know the amplitude is decreasing. So any wave that undergoes damping, their amplitude will decrease. The wave becomes weaker eventually. Next, the other one will be resonance. Okay, resonance, we realize that it is a system where any object, for example, glass, experience forced oscillation. Where the forced oscillation came? It came from sound. Let's say a sound wave going hit the surface of a glass, the glass will vibrate. You should know that inside glass there is molecule. The molecules are called silicon dioxide, right? So glass molecules also will vibrate. Glass molecules will vibrate at a frequency called natural frequency. So any particle vibrating in a solid object, they are vibrating at a frequency called natural frequency. So particles in a solid object are vibrating in a frequency called natural frequency. Due to forced oscillation from the sound wave going to hit the surface, the whole glass will vibrate. So due to forced oscillation, an object started to vibrate, right? When they vibrate, what happens? They will vibrate at a certain frequency. So when the frequency of vibration of an object equals the natural frequency, resonance occurs. At this point, the amplitude of the particle's vibration will increase, and if it's a glass, the glass will shatter. All right? It's a bridge also will collapse. All right? So yeah, according to Barton's parallel system, two systems with the same length. All right? When they have the same length, they'll experience the same period of oscillation. See these two. When they experience the same period of oscillation, they experience the same frequency. When they have the same frequency, they will experience resonance. For resonance, idea is two systems with the same frequency. Once they have the same frequency, they'll experience resonance. All right? See, this one have different length, right? So it's not going to experience any form of resonance with the other system. I think because they are different length, you can say that. So what happened here? No resonance because all the other pendulums are having different length. Because once their length is equal, period of oscillation become equal. So they'll have same frequency. What happened? They will experience the same resonance. So this is another resonance, right? There's a sound wave with a high frequency making the glass to oscillate. When the glass oscillates, it will shatter now because the glass experiences resonance. Boom. Right?